one arm requires infinite trial.
Yeah, you can do some statistical bounds, so you don't have to do it infinite number of times, and you just need to stop at certain point and you say, oh, this is the error gap. Yeah, so when we solve it, optimally solving it doesn't mean that you have to get to that point, but you can approximate with a certain epsilon value equation, and you do that.
And also, we just need to pick like the most valuable arm, right? We don't need to estimate the mean exactly.
Yes, it is. I mean, if we accept epsilon error, because anyway it's follow the sensor limit theorem when we try to draw the distribution from the trial.
But what you said is you don't need to accurately know the value, so you just need to see the order. If you know the order, you can just pick the best arm straight away.
So you can just splice the prior knowledge. So
Yeah, but your prior knowledge can be wrong. But here's the thing, right? So in the worst case, you're not going to be able to learn the best optimal solution. So because of this, we have a very different goal. So in Martian Bandits, we don't look at so our objective function is not as a classical optimization function, which is try to maximize or try to do some competitive ratio optimization. Instead, what we do we're gonna try to next slide. I will define it more accurately. But what we try to do is to design an algorithm which tries to get as close as possible to the optimal solution. And what I mean by trying to get as close as possible, because at the beginning, so this is the optimal solution. Okay, this is where optimal solution's performance goes. We are very at the bottom at the beginning, okay? But it starts to converge quickly, as quickly as possible. So if somehow we can prove the convergence rate is fast enough, then we are good. Okay? So that's the whole idea behind this. It's a high level explanation of the idea. So how to do so? So what we're going to do is we're going to do something called the regret. So the regret is the gap between the performance of the optimal solution, the technical optimal solution we cannot achieve at all, and the gap of and the performance of our solution over time. Okay? So if this gap is nice, well behaved, then actually we say that our outcome is good. So let me show you something. So I just realized I should let me try to draw this something. Can you turn on the light, please? Just quickly. So if you are familiar with optimization, right? So usually what you have is this is the optimal solution of the problem. And usually people want to look at something called competitive ratio, meaning that you are somewhere here, let's say 1 minus epsilon times the optimal solution. Okay? So this is typically people want to achieve. Like you take the ratio of the performance, and it has to be at least 1 minus epsilon. And everybody is happy in optimization. What we try to do is to beat this one by saying that yeah, we can start with something very low here. We're gradually getting better closer, so the gaps can be smaller, average gap can be smaller over time. So actually this is something we call it, this is a sublinear difference. And you put the word difference as a regret, so this is what we call regret. Then sublinearity is a bit better than competitive ratio. Because competitive ratio is actually means that the gap is always linear. The gap is always epsilon of the optimum. Okay? It's always linear. So we try to have a sublinear gap. Is it clear? Good. Okay, so yeah. So this is exactly what we are aiming for. To get the regret something here. So something about the request. Okay? And what happens if we have this? Once we call something, we can define so let me. Sorry, I don't like animation, so let me show the whole slide straight away. So now the goal is to have this regret as small as possible. So one way to do that is to look at the average regret. Okay? So the regret is the gap. Remember the gap of optimal solution and our optimal solution performance over time. It's cumulative over time. But you divide this gap by the number of time steps, you get the average regret. And if this average regret of your algorithm, of our algorithm, converges to 0, then you can say that it is a no regret algorithm. So this term, no regret, is quite funny. It comes from game theory. It doesn't mean that there's no regret as the name suggests. It just means that the average regret converges to 0. So a little bit misleading, right?
Yeah.
But
Should be like vanishing regret.
yeah, vanishing regret or something like, or vanishing average regret, not even the regret, average regret. Yeah, but the word no regret, it started. So Hannah used this term back in 1957. So it's very old term, and people cannot really get it. So a very simple example to show you that what does it mean. So for example, if this is a time horizon, you run it for 100 times, 200 times, so on and so forth, and you have an algorithm, that you know that the regret is always some kind of form of the square root of t, where t is the time horizon. Then if you take the average regret, square root t over t, then you will see that this is clearly converging to 0, right? As t converges to, as t tends to infinity. And this is an example of a very clear example of no regret algorithm. Yeah? So how to achieve no regret algorithms? How to? So I just want to show you one algorithm because there's out there so many, but this one is a very beautiful one. It's called UCB, and this has a very nice property, which is it achieves no regret guarantee. And the proof behind it is also very nice. So let's see how it looks like. It has a very strong assumption. It starts with the following. It says that all the rewards out there are bounded. Okay? They have finite supports. In this case, you can assume that all the regrets are between 0 and C, some C value, C typically 1, just to normalize things. It has an initial phase, so at the beginning, it pulls all the arms once, just to try out, just to get some value. But actually, you can get rid of this round later. And the reason you might want to get rid of this is if you have a very big program, you have like millions of actions out there that you don't want to lose this initial round. But for now, just assume that the model is a toy program. That's going to be k number of arms is k is 100 or 1,000. Something like that. Okay? So then we can afford to do that. And then after the initial phase, what you're going to do is you're going to calculate something called UCB index. And here's the way to calculate the UCB index. So each arm